So a new feature of ease is that it will allow you to define a substance that is an ideal gas mixture and then use that ideal gas mixture that you've defined in any of the built-in heat transfer or component library procedures that already exist. So in order to define an ideal gas mixture, you need to use a directive. So at the top of your ease program, you would use the directive $IGMixture. The easiest way to use any directive is from the directives information palette. So we'll go to options, directive info, and we'll scroll down to $IGMixture right here, and then you can see it gives you a palette down here that you can use to set up your mixture. So you can have up to 6 different ideal gas mixtures that you've defined. We're going to start here with mixture 1. If I want another one, I would just increment this counter up and down, and you can see the number right here goes up and down. So let's define our first one, IG1. Here you define the number of components. We can have as many as you want. Let's have 4 components. And then down here you're going to enter the composition of the mixture. So this would be the different components as well as their mole fraction. So this might be something like, I don't know, 20% nitrogen, 50% argon. Let's make this something different, maybe xenon, 20% xenon, and then everything else is going to be CO2. And you can see up here the directive statement changes in response to what you're setting up down here. So if I paste this at the top of my ease program now, I've just defined a substance called IGMixture 1. If I use that substance then anywhere, I can use it in all of the property functions, I can use it in all the heat transfer functions. So for example, maybe I want the enthalpy of this. So let's do H equals enthalpy of IGMixture 1 at T equals, let's see, my unit systems are Celsius, so maybe 100 degrees Celsius. And this should just work in the same way that any substance would work in. Oh, that was not what I wanted. So calculate, solve. There's the enthalpy of that mixture. And same for any other thermal property that you might want. What's even kind of nicer about this is I can also use it in any of the other libraries. So here, let's go to the heat transfer library, and maybe I'd like to know, I don't know, what the pressure drop of this mixture is if it were flowing through a pipe. So we'll pick the convection, and we'll come down here, and this is internal flow, dimensional. So this is a pipe. Let's just paste this one right in there, and you can see instead of air here, I'm going to use IGMixture 1 at some temperature, 20 C, some pressure, 200,000. What am I in kilopascals? So maybe 200 kilopascals. Mass flow rate is going to be 0.02 kilograms per second. The pipe diameter might be 0.02 meters, so 2 centimeters, and let's make it 10 meters long, and we'll make it smooth so the roughness is 0. So when I run this now, it's going to use this just as if it were water or CO2 or any other substance, and you'll find that the delta P is 4.46 kilopascals. You could use it also in the component library to run it through a turbine or a compressor or whatever else you want. In a similar fashion, there's now a natural gas mixture that you can set up in the same way. So if you're using natural gas, obviously natural gas is a mixture. There's a standard natural gas mixture, but if I go to the directive information here, and we'll go down to $natural gas 2, and you can see it's pretty much exactly the same here. There is only one natural gas, so natural gas 2 here, and the default concentration and composition is set up here. But if you want to change this, you can change it. It's just exactly the way that I've done it here. And if I paste it, so let's paste it in here. Now I can use natural gas in the same way. So let's do H2 equals enthalpy of natural gas 2 at T equals 200 degrees Celsius. And it should just take that like any other substance and give me back the enthalpy.